Hello everyone, welcome back to lecture series on Introduction to Computational Fluid Dynamics. Uh, in last session we discussed about discretization and types of discretization and difference between continuous and a discrete system. So today we are going to start with application of Taylor series, which we come across in finite difference methods. How we are going to apply finite Taylor series to develop finite difference equations. So today we are going to start with Taylor series. We'll try to develop first order finite difference equation and backward difference equation and central difference equation for a simple problems. So what is a Taylor series? So the purpose of this Taylor series in CFD is to convert the existing partial differential equation into algebraic difference coefficients at a discrete points. So we'll be representing the discrete points. At that discrete points, we try to apply the concept of numerical methods to develop an algebraic difference equation or algebraic equations, where the solution is purely dependent on values of those particular parameters at that point. So consider a continuous function of x, f of x, which has derivatives all over the x. So using Taylor series, the value of x plus delta x or f of x plus delta x can be obtained using this formula. F of x plus delta x is equals to f of x plus dou f by dou x into delta x, dou square f by dou x square into delta x square, plus and so on dou n x by dou x bar n delta x bar n by n factorial. So this is the Taylor series which we use in developing finite difference equations, where delta x is the increment in value and f of x plus delta x is increment or change in value of function, change in function. So what are the finite difference equations? So let us consider a discrete domain, so which is having, just like earlier in previous session we have discussed about representation, let p be the point, delta x delta y be the interval in x direction and y direction respectively. Let I comma j be the location of point p. Now if I consider u to be a velocity component at point I comma j, and I want to calculate velocity at I comma j plus 1, so that I am representing with u I plus 1 comma j. So u I plus 1 comma j is at point I plus 1 comma j. Whereas u I comma j is nothing but velocity at point I comma j. Now if I apply Taylor series to this, if I apply Taylor series to find this, so to apply Taylor series, let's say what is delta x here, I plus 1 comma j, the value is changing in x direction, so I'll take my distance or incremental value to be delta x in x. So let me apply Taylor series to this and find out what is u I plus 1. Now u I plus 1, u I plus 1 comma j will be equals to or will represent f of x plus delta x, and u I comma j represents f of x. Represents f of x. Now let us try to apply Taylor series for this particular velocity and identify the equation or develop the equation for that. So if I do that, I got ui plus 1 comma j is equals to ui comma j plus dou u by dou x, because variation is with respect to x direction. So dou u by dou x into delta x, dou square u by dou x square into delta x square by 2 factorial. Then I have dou cube u by dou x cube into delta x cube by 6, that is 3 factorial, plus and so on. So by applying Taylor series, we are going to end up with this kind of equation for the velocity at point I comma I plus 1 comma j. So if you rearrange these terms, what I can do is ui plus 1 comma j minus ui comma j. If I write it on the right hand side, what I have is dou u by dou x into delta x. Now the purpose of writing or finding out dou u by dou x or dou square u by dou x square is to rewrite the equation, the governing equations, in analytical form, or which are analogous to discrete ones. So algebraic equations I need to represent. So for that I am converting them and trying to rewrite them. So dou u by dou x into delta x, or what I can do is I can write this as dou u by dou x at I comma j is equals to ui plus 1 comma j minus ui comma j minus, okay, I'll write it into delta x, minus dou square u by dou x square into delta x square by 2 factorial plus, or dou cube u by dou x cube delta x cube by 3 factorial plus and so on. This is okay. I can write the equation. Now if I rewrite this, can divide throughout with delta x, divide with 1 by delta x. So what I can do is I can rewrite the whole equation in this form, where I have dou u by dou x at I comma j is equals to ui plus 1 minus ui minus 1 by delta x, and dou square u by dou x square into delta x by 2, because it is divided by delta x again, and dou cube u by dou x cube into delta x square by 6 factorial. So all this, if we assume to be error, with the minimum value as delta x, so we can rewrite this equation as error plus this equation is equals to dou u by dou x at I. So error is generally represented with order of delta x here, because the minimum value here is delta x. So you can rewrite this equation as dou u by dou x is equals to ui plus 1 comma j minus ui comma j by delta x plus O of delta x, which is order of delta x, that is the error. This represents error. So based on this, we can say that this equation can be called as first order finite difference equation. The above equation can be called as first order finite difference equation, since we are using the right side of I comma j, since the equation uses right side of I comma j, we call it as forward difference equation. And since inside the O we have delta x, we call it as first order accurate. So this is the minimum value inside the error what we consider. So order of equation is, or order of accuracy is delta x, and the equation is called forward difference equation. Now similarly if we use the Taylor series and apply for ui minus 1 comma j to find out ui minus 1 comma j, that is in the grid, what I'll be doing is I'll be using the left hand side of I comma j to solve it. So u I plus 1 I minus 1 comma j equals to u. Here my delta x will become minus delta x because it is on the left hand side of the point. So delta x will be now minus delta x. So the equation can be written like this. Now similar to what we have done in the previous case, if we apply same thing, we'll get dou u by dou x is equals to u I comma j minus u I minus 1 comma j by delta x plus order of delta x. Now this equation we call it as finite difference equation in Rayleigh difference form, since it uses left hand side of point I comma j, and it is having the order of accuracy as 1. We call it as first order of accuracy because delta x power 1. So this is called Rayleigh difference equation. Now let us move to the last part of our session, which is central difference equations. For that, let us consider both, that is ui plus 1 comma j and ui minus 1 comma j, which we considered earlier. Now if we subtract these two, that is add a minus, minus, minus. So this minus and minus gets cancelled, this minus whole square, right? So you will be left out with minus and minus will get cancelled. So you will be left out with these terms. These terms will get cancelled. Sorry, these terms will get cancelled because of same magnitude and different signs. So you will be left out with ui plus 1 minus ui minus 1 comma j is equals to 2 dou u by dou x at rate into delta x, plus if you observe, this is order of delta x cube, order of delta x cube. Now if we rearrange them, what we get is dou u by dou x at I comma j is equals to ui plus 1 comma j minus ui minus 1 comma j by 2 into delta x plus order of delta x square, plus order of delta x square, because delta x cube by delta x will be delta x square. So if you observe, for same dou u by dou x, we are getting higher order of accuracy, that is second order of accuracy. So accuracy of solution is of second order, and this we call it as central difference method, since we are using both right hand as well as left hand side of the point P to develop this particular equation. So subtracting forward or rearward from the forward equation, we'll get this. So the order of accuracy, as I just mentioned, order of accuracy is 2, which is called second order of accuracy, and small change, guys. This is to be second, delta x to the second power, so it has to be second order accuracy, and this will be the central difference equation, since we are using both right hand side as well as left hand side of the point P on the grid. So in this session we started with finite difference, that is Taylor series, followed by application of Taylor series to find out or to write forward difference equation, rearward difference equation, and center difference equations. Thank you all. Thank you very much.